Okay, see you. And now I introduce the last speaker of this morning, Anupam Das, who will speak about ontological strength of confluence and the normalization for cyclic proofs. Please, Anupam, go on.
Okay, hi. Can you all see my slides? Is that okay?
Yes,
I assume you can because I can see it on my other device.
You are mute, Anupam.
Thank you. Yeah, so thanks again to the organizers for organizing the conference. It's a difficult time, so we will appreciate it. So this work builds up on a program of research I've been pursuing for a while now, which is to try to understand at a deep level the strength of cyclic reasoning. Now, we've already had a talk on circular proofs this session by Koji, so at least some of the preliminary work has been done for me. But I always like to start with an example, and I especially want to show this example because it's my new favorite example. So this is in the world of circular proofs as type systems. So proofs as terms and propositions as types. And I'll walk you through this a little bit. So see this as a typing derivation, and the only type I will care about is the type of natural numbers, which I write n like this. And so let's think about this derivation. Well, it takes two inputs. Let's call them x and y. And the first step is a conditional. So what does the conditional do? It checks, you go into this subderivation if x equals 0, and otherwise you go into this subderivation. Now what happens if x equals 0? Then we just run the proof in the square on y, and it turns out this computes successor y. What happens if you go up? Well, this is where something interesting happens. Here you run something on x minus 1 and y. And then what happens is this bullet is a bit like a recursive call. It says, go back to this point here and run the entire program on x minus 1 and y. And then in fact, we have a cut, which then feeds that into another input with, again, a recursive call. So in fact, if you look at this and you stare at this, you can distill the following equational program from the derivation. So there's some circularities in it, but you can distill the following equational program. So this is what happens at 0 and what happens to successor x. And if you stare at this and you try to, you can see that this is clearly a well-defined function because we're just doing induction on x, a recursion on x. And in fact, it turns out that this computes the function 2 to the x plus y. So this is an example I found with a co-author of mine, Gianluca Cusi, on another piece of work. And if you know something about safe recursion and implicit complexity, this is a very interesting example for you. But the key thing to note here is this derivation here was non-well-founded. It has some circularities in it, right? And in general, circular things like Turing machines, they don't necessarily define total functions. So why in this case was it well-defined? And this is sort of the recurring theme in circular proof theory. So if we're in type systems, we're talking about well-definedness. If we're talking in predicate logic, we're talking about soundness and so forth. In general, we want to distill a correctness condition from these non-well-founded proof objects. So another thing I'll say before I get onto my own work is I think there's a lot of talks on circular proofs that very deep inside in a particular area, but there's one thing I should point out, which is it's a very, very large multitude of areas and at least 3 very important lines of research focused in these 3 columns. And there's a lot of research in each of these areas. I'll point out maybe just a couple references because they're very pertinent. I would argue that this paper of Nowinski and Valukiewicz, Games for the Mu Calculus, was arguably the inception of the area. It was this that inspired proof theorists to consider circular proof objects, or certainly regular circular proof objects. And of course, all this work on type systems are very relevant are precursors to what I'm doing today. And in many of these areas, even with different subject matters, there's an underlying question that is often posed, which is colloquially termed the Brotherstone-Simpson conjecture. Are cyclic proofs and inductive proofs equally powerful? So in a sense, we sort of have an idea that inductive proofs can be translated easily into cyclic proofs, let's say easily in inverted commas. But the other way around is usually a more difficult thing. And certainly calibrating the strength of cyclic inductive proofs has many consequences in each of the settings at hand. So if you're in modal logic and you can prove something like this, then you might be able to distill a completeness result for an axiomatization. And there are other applications in other areas. So this very almost vaguely worded question is quite is a recurring theme in circular proof theory. And just to give one example from my previous work, which motivates the current work, is in the setting of arithmetic. And in arithmetic, we now understand the question very well, but these two results maybe showcase the nuance of the question itself, because it matters what we mean by equally powerful. So already Alex Simpson showed that a version of arithmetic based in circular proofs is equivalent to pure arithmetic. But then a work of mine, I refined that, and I actually said that in fact they are equivalent, but if you start looking at the quantifier complexity involved in the proofs, cyclic proofs are more succinct than inductive proofs by exactly one quantifier blocking complexity. Now, I don't want to talk about the arithmetic stuff too much or these classes sigma n, because some people might be familiar, some people aren't. If it's not so familiar with you, don't worry about it. The motto here is that cyclic proofs do buy you something if you look carefully enough. And we see that in lots of other areas, and this was also maybe relevant in Koji's talk. And so in this talk, we're going to talk about type theories, and it will become relevant why we're talking about type theories in a moment. And the starting point for this, for me at least, was to look at Gödel system T. And to understand Gödel system T, one must first understand Church's simple type theory. So I imagine many of you have seen this before, but as a reminder, we'll work with only the finite types or the simple types, which are generated from a single base type n, and you should think of these as ranging over the natural numbers. And we have an arrow type, and we'll consider simply typed languages. This will just be a set of typed constants or combinators, and terms as usual are formed by typed application. And a simple type theory is now just given by a set of axioms and rules. In this setting, we'll always assume intentional equality. I don't want to go into that too much, but for technical reasons, that's what makes the results work. If you know what that is, good for you. If not, don't worry about it too much. And the simplest possible example is something you've probably at least heard of, which is combinatory algebra. And combinatory algebra is a simply typed theory that within its language has infinitely many constants for every pair and triple of types sigma tau and rho sigma tau, and is axiomatized elegantly by just a bunch of equations like this. Now here I've omitted the type annotations of K and S. They can actually be recovered from the syntax, but for ease of reading, I'll omit those. And this is a very nice example. It also showcases how we interpret these in the standard model. So in the standard model, we think of the natural numbers and higher order functions on the natural numbers. So as I said before, the interpretation in the standard model of n is just the natural numbers, and of the arrow type is just the function space from the individual types. And in this standard model, we have unique interpretations of each combinator, each constant, by just taking these equations as definitions. So we just make those definitions, and it's not hard to see that this is well-defined now. So this is a good example. And then from here, we can easily arrive at system T by simply adding recursion combinators. So recursion combinators are axiomatized as follows. And if you look at it, all it's doing is implementing a form of recursion on a single numerical argument. So if your argument is 0, then you return a function you've already defined. And if it's non-zero, then you run a function that may have a recursive call, so on a lower argument. And finally, to finish the specification of T, we add some quantifier-free axioms and rules, which tell us that 0 and successor form a free and inductive structure. So we're getting pretty close to the structure of the natural numbers now. And why is this such an important theory? Well, mainly because of this famous result of Kurt Gödel. So I give the year is 41. I'm not sure exactly how early he did it, but I think this is the earliest known reference of this result. I state it like this, just so it's comprehensible to everyone. T is equiconsistent with pure arithmetic, but in fact, his interpretation shows a lot more. He gives a way to interpret all of pure arithmetic within system T. And the motto of that is that Peano arithmetic, this crazy theory with lots of quantifiers and logical complexity, can all be interpreted into this just equational theory, this quantifier-free theory system T that has a lot of computational power in the level of its terms. So the motto is that we can trade off quantifier complexity for abstraction complexity. And that is a really, really deep observation. And it's something that underlies lots of research in computational proof theory and computational logic over the following decades. And so in this talk, in this work, we're going to think about a circular version of system T. And once you see this result of Gödel, of course, the natural question is to then compare the circular versions of T and circular versions of arithmetic to build some sort of bridge between the cyclic proof subject of predicate logic and the cyclic proof subject of type systems. So one motivation here is to try understand relationships between two different worlds of circular proof theory. Okay, now when we're in circular proofs, it's very convenient to work in sequence style. And so sequence, we just have a list of formulas on the left and a single type on the right. And they compute, and we should just think of this as computing a function of type like this. And each rule can be construed as a constant. And by construing each rule as a constant, let's just make a very simple observation that every derivation can be seen as a term, and that affectation is actually a continuous affectation. As you go up the derivation, you're printing more and more of the term. This is going to be important because we're going to consider non-well-founded derivations later, so we need such an operation to be continuous. And just like before, we can have an equational theory here. And just like in the example of combinatory algebra, we get interpretations of these constants in the standard model. But this time we need to use a bit of induction at the meta level. The reason for that is to show that this recursor has a unique interpretation. We must do induction on the recursive argument. And maybe just one thing I didn't mention is that if we take this, unsurprisingly, this is just minimal logic with a single base type. And this just gives you number theoretic constants. So once again, to reiterate, system T is just the extension of combinatory algebra with minimal number theoretic features, in particular recursion and induction. And now we're ready to set up the non-well-founded system that we're going to consider. So the first thing is we can now talk since we have a system of rules, we can talk about coterms and co-derivations that are generated co-inductively from those. So a simple way of saying that is just we're now considering infinite binary trees generated from the rules, not just finite ones. And let's just make the point, because of this continuity of taking the combinatory approach, we can talk about the coterm of a co-derivation. This is a well-defined concept. And just like we saw in Koji's talk, we take the same definition of regularity or circularity. A co-derivation is regular if it has only finitely many distinct sub-co-derivations. Okay, and that means in particular, we can write it as a finite directed graph, possibly with cycles. And we can see these as having a semantics that are a Knight-Herborn-Gödel style partial function. So just a set of equations, and as a model of execution, we can talk about equational derivability. And in fact, that's exactly what we saw at the beginning of this talk. So when I showed this example, this is exactly what happened, right? So we have, this is an infinite tree where it has only finitely many distinct subtrees because the tree rooted here is identical to the tree rooted here, is identical to the tree rooted here. And this was our equational specification that we extracted from the proof. And this can just be done continuously by definition on the proof. So going back, oh, whoops. Okay, I can't go back very easily. Right, so let's see a very, very simple example. So this won't be a regular proof, but we can actually get, we can represent every type 1 function using a non-well-founded proof. Now this is a non-regular proof, it has no finite representation. So it's unsurprising from a cardinality reason that we can represent all these things. Just for time, I'm going to skip that. But the unfortunate thing is we can also represent lots of bona fide partial functions. So partial functions that are not well-defined total functions. In particular, we can represent unbounded search here, even with a regular co-derivation. And so the point of cyclic proof theory is to insert some sort of criterion for meaningfulness. So in this case, well-definedness of the partial function defined by a co-derivation. And for this, we introduce a condition of progress. And so if you were looking earlier, there were a lot of colors in the derivation. And what we ask for is that we can find in every infinite branch, so in this case, we have only one, we can find a sequence of ends that are related by the colors that is more of a principle for a conditional step infinitely often. And the idea is that this guarantees some form of infinite descent. If we go back to the example of unbounded search, there is no such thread. So if we try to follow this one, then the blue one ends up here. The red one ends up disappearing. And now we're left with a new n here. So there is no infinite thread that supports this infinite branch. And so this one is not progressing. And now we can just define our circular type systems, circular theories, I should say, in the expected way. We just take the progressing co-derivations that are regular as symbols of our theory, and we build up a simple type theory in the standard way. And in particular, we're going to consider the fragments delineated by the type level of types occurring inside a derivation or co-derivation. And these are, for Tn, this is a standard definition. It's the same as restricting the type level of the recursives. And so we just take an equivalent definition for circular T. And then one thing before we continue is we better state what we claimed and prove it. A progressing co-derivation computes a well-defined total functional. Now, I won't be able to go through the whole proof, but the idea is very simple and it abounds in cyclic proof theory at large. The general idea is we know the locally each rule preserves a good property, in this case, well-definedness of the function, well-definedness of functions. And so by contraposition, we can, if we assume the conclusion of a co-derivation is not well-defined, we can build an infinite branch of non-well-defined functions. And from here, we can get a progressing thread by the progressing condition. And to each n in the progressing thread, we can assign the least natural number that witnesses that non-totality. And by definition, we can see that this sequence will be monotone decreasing. It can never increase. But since it's principal infinitely often, it must also strictly decrease infinitely often. And that contradicts the well-foundedness of the natural numbers. And so this is the sketch of that argument. So then let's see one more example. So this is the well-known Ackermann-Peter function. It's defined by an equational program, just like this. And it's well known to not be representable in T with recursion at type 0, because those are just the primitive recursive functions, and Ackermann-Peter is infamously non-primitive recursive. On the other hand, we can represent it in CT 0, because if you see, we only use n's all the way through the derivation, and we just have a very complex sequence of back pointers. The circular structure is quite complex with many intersecting cycles. So the motivating question here is, what is the relative abstraction complexity of functionals in T and CT? And this is what this work addresses. So I won't have time to go into all the technical details, but I want to, because especially since we're FSCD, mention a little bit about the rewriting theoretic tools that I use to address this problem, and then I'll just state the main results. So the first thing we'll try to do is we'll take those equational axiomatizations and we'll just recast them as a rewrite system by orienting them from left to right. Very standard idea when we're talking about system T. But now note that we're talking with this is a rewriting system on coterms and co-derivations, not on terms. But nonetheless, we can show that the system is confluent by adapting some known arguments. It's important that we do not conduct an induction on the structure of a term, because remember, terms are non-wellfounded, so they do not have an inductive structure. But we can recast standard arguments by induction on length of rewrite sequences instead of structure of terms. I will be, for a lot of these results, saying something in the brackets like this. If you don't know what that means, don't worry. It will become relevant soon. So we can establish confluence. And what does this mean? This means that computation is deterministic, which is something that will be useful for us in the models we're about to define. So next, we're going to define a model. And just like we might define like a term model from the normalizing terms in system T, we can actually define a model of coterms. So we can define a type structure whose domain is a set of coterms. And here we're just recasting the well-known structure of hereditarily recursive operations, but now taking coterms as our programming language, regular coterms, I should say, recalling that regular coterms form a Turing complete set. So this is just sometimes called a logical relation, but I like to see it as a type structure that's defined using impredicative extensions. And using this, we can actually show as a corollary of confluence that this structure satisfies the induction principle, or at least for each formula, it satisfies the induction principle. And now that we've got that, if we have Tate's normalization result, for example, we immediately have that it's a model of T. So the only thing left is to show that this is a model of CT. And this is indeed what we show. So we're able to show that for each CTN coterm, T is an element of the model at the corresponding type. And what's the main idea here? Well, it gets a bit technical, but the main idea is to formalize the soundness argument I showed you a moment ago, but with respect to the hereditary recursive type structure. So if it's sound, it's true, and it works in all models, but we're going to formalize it with respect to this particular model. The reason we're going to formalize it in this particular model is because we can actually then arithmetize it, as I will mention in a moment. We can show that this branch is well defined by minimization principles. It's rather important to control logical complexity by this trick of approximating thread progress, but I don't want to talk about that today. And so as a result, we get that HR forms a model of CT. And in particular, as a consequence, by the definition of the type structure, we obtain a normalization result. T is weakly normalizing with respect to the reduction relation for each term T. And now I want to point out why I'm writing all these weird annotations in brackets. This is not just because I'm a meta-mathematical nerd, which does happen to be the case, but there's actually a good reason for it. Since we've arithmetized these results within appropriate fragments of second-order arithmetic, we can actually apply very well-known program extraction techniques, indeed, like the dialectical interpretation of Gödel himself that I mentioned at the start of the talk. And this gives us almost for free, because we formalized it in appropriate, because we controlled our reasoning and formalized it in suitable fragments of second-order arithmetic, we actually inherit an interpretation of CTN into Tn+1. Mimicking the result in arithmetic. In particular, we can say that for the type 1 functions representable in CTN, they're also represented in Tn+1. And so if you take the unions, we have that actually CT and T represent the same type 1 functions. So these are the main results of this work. I'm going to blast through a few further results and some other consequences and related work, but I don't want to dwell on them. So first, in the same work, I didn't have time to talk about it, but we're also able to establish strong normalization. This is by adapting Tate's method to a coterm model instead of a term model. We show this is provable in RCA₀. We don't refine the type structure. We also show type T continuity, which extends the equivalence of T and CT functionals to type 2. Again, we don't give a strong mathematical treatment there. In parallel work that's not in here, but it comes at the same time, we actually establish a converse, which is in a way a bit harder. You have to do a bit more proof theory. But this means that Tn+1 and CTN are equiconsistent, really running through the themes that we saw at the beginning of the talk with Gödel's result, with the results about cyclic arithmetic. And we're also able to show using meta-recursion-theoretic methods that CT and T actually represent the same functionals at all types. But that's not in this work. I point to the preprint for those results. And to summarize, we did interpret the CT into Tn+1, and by the parallel work, this is actually an optimal result with respect to abstraction complexity. I must mention a recent work of Kuperberg, Pinot, and Puss, who considered a variation of just the typing derivations with a slightly different type language, including Kleene star for list formation instead of n as a base type. And they, in particular, studied substructural considerations. They showed that the affine progressing coterms corresponds to primitive recursion. Primitive recursion really at type 0. And we're talking about the type 1 functions representable in that framework. Now, they also show a form of progressing coterms corresponding to the functionals definable in system T. And so in this sense, you can see our result as optimizing the result with respect to abstraction complexity and also given a bona fide logical interpretation. There's works only at the level of the functionals computed in the term language. And finally, there's a lot of work going on at the moment. As I said, my ultimate goal is to get a proof interpretation between cyclic arithmetic and cyclic T. This is joint work with Tom Powell, and there are some other interesting things going on. As we saw in the beginning, some examples that could be useful for complexity theory. That's work with Gianluca Curzi. And finally, trying to admit arbitrary inductive definitions. This can be done in many ways. There's certainly relevant work by Berardi and Tatsuta from 18, and work with a master student, Lucas Melgard. I think I'm out of time now, so thank you very much.
Okay, let us thank the speaker. Okay, I see the clapping going on. Okay, any questions? Maybe, Anupam, if you remove your condivision,
sure,
your sharing of the screen, I could see the. Okay.
May I ask a
Just
question?
to see if there was some. Alex Rice, please.
Yeah, so I just want to ask a quick question. So you showed that these cyclic proofs could translate into recursive formulae, or these recursive formulae on natural numbers. Is there a result going the other way, saying can all these recursive formulae be generated from a cyclic, or can some class of functions on the natural numbers be generated from cyclic proofs?
Yeah, so there's an elementary example showing that you can just simulate primitive recursion with cyclic proof. That's not very hard. And so somehow the containment of T within CT is quite trivial. The difficulty is actually to optimize the result. So that only gives you that Tn is contained in Ctn. In fact, I mentioned right at the end, there's a parallel work where we get the optimum result, which is that Tn plus 1 is already contained in Ctn up to the type n plus 1 functionals definable in it. And so that requires some more sophisticated structural proof theoretic methods. But yeah, the motto here is that this really is a tight result. We calibrate the power of Ctn and Tn plus 1 as being equivalent. In particular, they're equiconsistent.
Okay, more questions? I have a question. So the cyclic idea was started because it was simpler to find proofs without cut. Is there any, even if of course just the simplest theorem could be proved in cyclic proofs without cut, while the more involved result still do require cut. Do you see any similar advantage in type theory for using the cyclic approach in type theory?
I think I do. I mean, so if I may just go back to some things I showed you. So right at the, so I think I showed two examples that might be pertinent. One is this example of the Ackermann function. So the Ackermann-Peter function. Like I said, you can't, a program for this in system T must have arrow types. We know it's not typable with just primitive recursion at type 0. And so somehow these equational programs that are quite, are often quite intuitive when you're doing programming, might be realized by these cyclic functional programs in a more readily, right? These sort of substitutions during recursion, we kind of know we can translate them to type 1 recursions, but it's a bit ad hoc. Whereas here, this program just clearly implements that equational program. So it's quite a natural idea. Another example, which is maybe more pertinent, is this one, which is showing that we can actually get more computational expressivity, even at the level of complexity theory. So you can actually annotate this derivation and it will satisfy a certain condition in implicit complexity known as safety, which usually guarantees that you can only define polynomial time functions. Whereas here you get this expressivity just by allowing cycles. So, you know, somehow I think it allows you to express more things more naturally, more succinctly. So I agree there's no problem of proof search here because we're doing, you know, type inhabitation isn't the problem we're looking at, but there's still an interesting problem of just expressing natural programs within, say, a functional programming language. And this approach could be useful for that.
I see. You reduce the nesting of arrows.
Moreover, we can represent equational programs more easily.
Okay, so essentially you have one level less of the
precisely
nesting of arrows.
Just like the arithmetic result. So we're trying to recreate that result in the level of type theories.
Okay, more questions?
I'll stop my share.
If there are no more questions, I think the session is ended. Let us thank all the speakers and see you, we hope in person someday. But okay. Thanks to all the speakers and have a nice lunch. It depends on some people are quite early or quite late and in the world, so it's harder to find the good formula for everybody. But see you soon. This will be, I think, something all of us would agree about. So the next session continues in half an hour. Okay. Have a nice break and see you.